In this section of chapter 4, I'm going to discuss names and reactions of alkynes, enwynes, and enol. First, we'll talk about alkynes, and as we know that alkynes have triple bond, carbon-carbon triple bond. An enwyne would have N stands for alkene, YNE for alkyne. So you'd have two different functional groups. This is the alkene functional group, carbon-carbon double bond, and C triple bond C is alkyne functional group. So when you have both these functional groups, then at the end you'd have N and YNE. If you look at the naming of the compound given at the bottom, you can see this is a carbon-carbon long chain having 8 carbon atoms. Let's count it: 1, 2, 3, 4, 5, 6, 7, 8. I numbered them. Now the question is why we started numbering from this side. The reason is your functional group has to get the smallest possible number. In this case, functional group is YNE, alkyne. So by using 1 on the extreme right, then you had 2, 3. At the third location, you have triple bond. So you have a substitution group, which is a methyl group, at the 6th location. So that's why we would name it as 6-methyl. That's the methyl group. Then is octyne. Octa means 8 carbon compound. Oct 3-wyne, because the location of the triple bond is the third position. Now let's name an NYN compound. Now, in other words, it has both triple bond as well as a double bond. This is the triple bond and this is the double bond. Now, numbering starts from the end that is nearest to the first multiple bond. Doesn't matter whether it's a double bond or triple bond. So I had to start numbering from left hand side because that gives the smallest possible number to a multiple bond. In this case, it happened that multiple bond is an alkyne functional group. So altogether we have 9 carbon in the longest chain, and we have a substitution group attached to the longest chain, which is a methyl group. Obviously these are all without hydrogen. So with 9 it's nonane. Nonane for alkane, non-wyne for alkyne, but since you have both alkene and alkyne functional group, so this would be NYNE. So 4-methyl non, then the 7th location you have alkene group, so that's the 7th location where the alkene group begins, 7N and 1YNE. So that's the name of this enwyne compound. Now, when there is a choice of numbering a multiple bond, C double bond C receives the lower number. So in other words, in this particular example that's given at the bottom, in the second location, if I start numbering from the right hand side, second location we have a triple bond or alkyne. On the other hand, if I start numbering from left hand side, my second location would have a double bond or alkene functional group. So the rule says that if that happens, in that case, you give priority to carbon-carbon double bond. So that's why we accepted the bottom set of numbering. Now, there are 7 carbon in the longest chain that contains both the functional groups, both alkene and alkyne. And 7 means hept. And of course, you'll have to have NYNE at the end. Now, the location of the EN or alkene functional group is 2nd position, and YNE is the 5th position. So that's why it say hept 2N 5 YNE. Addition of hydrogen and Cl2 is very similar to the addition of H2 or halogen in alkenes. So just to remind you, hydrogen addition takes place in syn manner. Syn manner means both hydrogens get bonded from the same side of the plane. Whereas in case of halogen, the addition happens in anti-fashion because it forms a complex which is bromonium ion, chloronium ion, and so that's why addition happens in an anti-fashion. Now let's first talk about addition of hydrogen. Hydrogen needs a catalyst, and since hydrogen gets attached to the surface of the catalyst, so if I consider this to be catalyst, then alkyne, in order to react, has to come close to hydrogen, and then hydrogen gets bonded. So these two hydrogens would get bonded from the same side. So whenever there is a possibility of cis-trans isomer formation, you're going to get cis isomer in this case. Now these are the groups bonded to the triple bond, carbon-carbon triple bond, and others are hydrogen. So they would be on the same side, and that's why it would be a cis isomer. Now here we are showing you in right orientation because this angle is 120 degree. sp2 hybridization, we all know that when there is a carbon that has a double bond, then we count double bond as a single bond or one pair of electron, and overall you'll be counting around this carbon 3 pairs, and that gives you sp2 hybridization and 120 degree angle. So in other words, it would look like this. So these are the groups bonded to the double bond, and they're on the same side as hydrogen gets bonded. Now this is cis because there are two groups on two carbons and they're directed on the same side. So 6, and my longest chain, I'm going to show you that in naming compound, again, you look for the longest chain that contains the carbon-carbon double bond. Let's use the other pen so we can better see it. So always, this is the longest chain. Longest chain must contain the functional group. In this case, carbon-carbon double bond is the functional group. Now, remember how to number these. You number it in such a way so that the functional group gets the smallest possible number. So obviously that tells me my numbering should start from right-hand side. So 1 in here, 2, and then you'd have 3. Let's write down 3 at the bottom because to make some room. 4, 5, then you'd have 6 and 7. Now this gives the smallest possible number to the alkene functional group. So that's why it's 3 in. On the third position you have the double bond. Now substitution group that is attached to the longest chain is methyl, and is attached to the 6th location, so it's 6-methyl. The longest chain has 7 carbons, so it's heptene, but the location of the double bond is 3rd position, so that's why hept 3 in. And then you need to also write down whether it's cis or trans, because there is a possibility of both, but in this case we do get cis because hydrogen gets bonded from the same side, and that's the final product, cis 6-methyl hept 3 in. Here we are going to see the addition of chlorine, and this would happen in anti-fashion, so that one Cl would get bonded from the bottom and the other Cl would get bonded from the top. And also there is a restricted rotation because of the presence of double bond. In other words, they're going to stay like this. One Cl on one side, the other Cl on other side. So in other words, in this case, if there is a possibility of cis or trans, you're going to get trans isomer. But you have to be careful about this particular compound. Here you have one substituent group attached to carbon-carbon double bond. This is the second one, this is the third one. When you have 3 groups, cis or trans would not work. Then you have to consider E or Z. Remember about E or Z? Let's split this molecule into 2 halves. Now, assign priority on the left-hand side. Cl has a higher atomic number, so it gets the higher priority. So I'm going to write down as H. The carbon, that gets the lower priority. I'm going to write down L. On the right hand side, Cl has a higher atomic number, so it's got a higher priority, so I have to write on H. And hydrogen has lower priority, L. Now you can look at the location of the high priority group. They're opposite to each other. When they're opposite, it's E, not Z. So E, 1,2-dichloro, again here the longest chain has this many carbon atoms, 1, 2, 3, 4, 5. There are 5. So it's going to be pent 1-in. That's the ending. Then you would have 1,2-dichloro pent 1-in. Now the reaction of alkyne with H2O. Again, alkyne would react with H2O in this manner. H should be attached to the carbon that has the larger number of hydrogen, which is like Markovnikov's rule applied to carbon-carbon double bond. So this hydrogen goes to this carbon which has a hydrogen, but the other carbon doesn't have any hydrogen. And keep something in mind, often students make mistakes that they try to bond hydrogen to other carbon, but keep in mind other carbons are saturated with hydrogen, so it cannot accept any more hydrogen. So only place it can go would be carbon-carbon double bond or triple bond. In this case you have a triple bond, then you look for carbon that has larger number of hydrogen as well as unsaturation or multiple bond. So on that ground, this hydrogen would get bonded to this carbon. Now that would result in CH2. That end would change to CH2. The triple bond would be broken. And then you'd have OH, that's the other part of H2O, gets bonded to here. Okay, so that's what you got now. Now this kind of compound is called enol because there are two functional groups, alkene functional group and OL is coming from alcohol functional group. So this is alkene functional group, this is the alcohol functional group. Now enols are not very stable. In most cases it would go into rearrange into ketone. What you're seeing here, I'm going to show you in a second, is not resonance, rather we call it tautomerism, because here an atom is moving. And let me show you how that happens so that you really understand that. It has some similarity with resonance, but it's not resonance. C, C, C. I have at the fourth carbon you have OH. I'm going to write down OH a little differently. O, H, so that's the fourth carbon. And then I have C double bond, C, H, 2. Okay, let's double check so that I haven't made any mistake in copying. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then OH. Now I'm showing you now how enol can be changed to a ketone. We call it enol keto tautomerism. The pair of electron that you have in between hydrogen, let me use a different color. Pair of electron that you have in between hydrogen and oxygen goes in between carbon and oxygen, because that's a good passage for electron, because there is a weak pi bond and that releases this electron pair, because otherwise carbon would have too many bonds. So it releases this electron pair onto carbon. So basically that would result in the following. Hydrogen gets out. This hydrogen gets out. Because when electron is gone, there is nothing to hold on to oxygen, because electrons are like glue. So now I'm showing you here, from here you get this. C, 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 that's the third. Fourth one would have C double bond O, that's the newly formed double bond. And CH2 would have minus. That minus is coming from the fact that this carbon-carbon double bond releases this electron pair onto CH2 in order to accept electron pair from OH bond. So now hydrogen gets separated as H+. So that's why it's not, in a strict sense, it's not resonance, even though it's similar to resonance. because in resonance you're not allowed to move any atom or break down any atom. They will all remain intact. Now this H plus then gets bonded to this this electron pair on CH2, and then it gives you this compound. And in this case, due to enol keto tautomerism, ketone structure is more favored. So you end up with 2-pentanon. Now we're going to discuss reaction of alkyne with sodium amide. NaNH2. Na is plus and NH2 is minus. And it would act as a very strong base. If you look at NH2 would look like this. 1, 2, so that's 6, 7, 8. So that NH2 minus. So this is NH2 minus. You can always double check. Nitrogen has 4 electrons solely on itself, and it gets 2 electrons from the shared bond. So it was 6 electron. And if you look at periodic table and count the valence electrons, so you'd find that there are 5 electrons in there, in the valence electrons. But in this, because of the sharing, it got 6 now. So it got an extra electron, and that's why it's -1. Now this is a very strong base, and it picks up hydrogen. It's a strong base, picks up this H plus from here. So that gets really basically gets bonded to this hydrogen, and you end up with NH3. And C triple bond C, since it lost its lost its H plus, it becomes minus with pair of electron. Now scientists or organic chemists can make use of this species in reaction like this. And this reaction, what you're seeing at the bottom, happens only with primary or 1 degree alkyl halide. 1 degree means this carbon is bonded to only one other carbon. For 2 degree or 3 degree, you would undergo dehydrohalogenation to alkene. In other words, it would undergo elimination reaction to alkene. So anyway, in this particular case, this double bond, this pair of electron gets attracted to the carbon, which has delta plus, and as Br is delta minus, it will be attracted to this carbon. When it gets bonded to the carbon, that carbon would have temporarily 5 bonds, and so it has to get rid of 1 pair of electron or 1 bond. It looks for the best leaving group, and it's well known that halogens are very good leaving group, and that's why it releases electron onto Br, and then Br leaves with this electron pair, and Br gives you Br minus. So that's going to be the final product. So you basically attach this alkyne group to an alkyl halide group where halide is gone. So basically you can extend the long chain of alkyne. So I can basically add 2 additional carbons as well as alkyne functional group by allowing it to react with an alkyl halide, where alkyl halide is 1 degree alkyl halide.